Oh, whoa. Now it's super loud. Can it be a little bit? It's like I'm scared of my own voice at this point. 1, 2, 3, better. All right. So I do understand where you guys stand. It's the second day. It's almost the end of the conference. Probably a party in the castle is where you want to go. So I have a slides of this tremendous amount of Haskell code. And they put me at the end of the conference. So, in order for our brains to survive, I've provided a few alpacas and llamas. So, kind of like if you see one, it's the time to check your Twitter, wander off for a few seconds. Like, other than that, please stay with me, all right? So, any sufficiently advanced technology is indistinguishable from magic. My point is that Haskell is a little bit like that. You can have libraries in Haskell which, for newcomers, they seem like magic. They do magical things, and you don't know how, but it somehow works, and you can do a lot of stuff with it. Now, this is the cool part of magic, because eventually, once you start using those libraries, at some point, maybe you will start researching like how they work underneath, what's the actual science or engineering behind them. And once you know a little bit of science in one library, all other libraries become intuitively how they are being designed. It's just brilliant. And my presentation is about that. So I'll be showing you a few libraries from Haskell World, which when they start using them, they seem a little bit magical, but once you understand the engineering point behind them, you also know how they work, and you become a better engineer. And my overall point I'm trying to sell here is that Haskell can be a general programming language, and you don't have to do Xylo, Hilo, Philo, most morphisms to actually be productive in it. You will notice that I beside my newborn, this is the thing that keeps me at night. So I'll be probably spending a lot of time there. My colleagues hate me for it. All right, so ASIN. ASIN is a library that allows you to do encodings, and so like encode and decode between your data types in Haskell and JSON. So here you have, some URL. If you go there for example, for euro, you'll get exchange rates between other currencies. Here, euro is your base, maybe some data as a string. A simple JSON, nothing really fancy about it. Now, for that JSON, I could pretty much create this structure which, I don't know, like directly represents that JSON, right? So the magic behind the ASIN library is that you can magically go between that JSON text and that structure for free. So this is how it works. We have our structure here, and we will have a function encoding example in which we construct our rates result data structure. Then we call this function encode on it, which gives us a text, and we will then later on print that text out to the console. And if you actually run this thing, it works magically. Nobody knows how. Well, we will learn how. Now it's the science part. Apparently, that I didn't show you the whole picture. Beside your structure, you also need to provide an instance to this type class, so that the first time you see type classes, you're like, oh, what the hell is that? Now you know what it is, and you know that this toJSON type class has a function encode. But there's another set of engineering behind it, because if your structure derives generic. And how many of you guys been on the first day at the generic workshop? A few folks, yeah, half of the room, right? So you know how it works, you understand, but you don't have to, right? You can slowly get into the underlying things behind the machinery behind the libraries, but that generic things create a representation of your structure from which it can magically create the instance for the rate result. And that's it. That's the old code that was needed to make this rest of this code to compile. It just works. What about going the other way around? If I have a string, so I have my structure, I read that string from file. I then call method decode on it, and that gives me a maybe type. So then I have to extract, for example, let's say base from it. If I decode it correctly, I get that base. If not, nothing happened. And yeah, we can run it, and it works. There's nothing new in the science department about that. There's just another type class with the decode method, and having a generic instance created for you, you get this function decode for free. So here's the first alpaca for you. You have to chill now. This isn't this bad. Like, it was supposed to be like 4 libraries. We just finished the first one, right? We might be like in 50 minutes, we'll be drinking beers. This is awesome. All right, so another library is called opt_parse_generic. So how hard do you guys think is actually, like, how hard is it to create a conference like Lambda World? Is it hard from like logistic perspective? I beg to differ. I think it's really, really easy. So the only thing you have to have is like a name for a conference, number of attendees, and the price of a ticket. And I actually implement a function that creates a conference. Done, right? What's the big deal? Now, I can test my function, it works, right? Jesus Christ, that was simple. So now we can go to production. I have a function that takes a string, an int, and a double, and creates a conference. It seems to work in a REPL. It's a REPL-driven development. So I run my main function where I take arguments, that's a list of thingies, so name, capacity, and price, and then I call my function. Obviously, this will not compile because capacity and price apparently are strings. So what can I do? I can just call the read on it, and yeah, it works. And yeah, it kind of like works, but whenever somebody just inserts something which is like, maybe they forget some elements, like here, like a price, or they were supposed to put an integer, but they give me a double, things collapse. So I wonder if like what opt_parse_generic will give me, what's the magical thing about it? Well, the magical thing about this library is the fact that you can have your little structure like here, like conference, which will hold all the arguments that you need for your function, and you can call this method getRecord, and it will give you exactly that object. So it will give you the conference with a name, which is a string, capacity an int, and price, which is a double. And now I can finally call my final create function and be done with it. And when you use it, you get all those arguments like the nice way, like you would normally run the command line program. You have the -- name, capacity, and price. If you forget one of the arguments, you will be informed that you forget the price, which is a double, and you get additional help. And I guess it's a pretty cool library if you start writing applications in Haskell. It's just a nice starting point. And you get all that for free. You get that function, getRecord, for free. Now, what's the science behind it? You might probably already see, because yes, it's exactly the same machinery as we've seen with async library. So we have our conference. We need an instance for a type class parse record, but we don't have to write it. The only thing we have to do is derive generic, and magically everything else just works. It's nice, isn't it, right? I hope it is. Is it? Yeah. A bit more magic. So here's the funny part. There's a lot of like cool things you can do with this library. You know, you have fields that are optional, or maybe fields which you can take like more arguments of the same name. It's all doable in that library. But there's one really cool feature, but it's weird if you look at it for the first time. So it's an additional bit of magic right now. So this is our type, and it's data constructor. And we know like the name was a string, and capacity was an integer, and price was a double. And now we do this. This. And you look at it and you're like, you know, Mother of God. What the hell just happened? Because think about it. Wait a minute. If that was a string, that's hopefully a type. Now I have a type which takes a value, or maybe a value is a type. And what's the question mark? Is that an operator? Is that a function running on types? Crazy stuff, but we're gonna get there. But the thing is, again, it's magic. For now, you just chill. It works, and it gives you a description for your fields, which is, I think, quite nice. Though it's weird if you see it for the first time. Okay, so it works. Another alpaca for you. chill, okay? Twitter. All right, another one. So this is now it's going to be a bit more heavy now. So servant. Okay, so servant is a set of libraries, I guess, that allow you to write HTTP server, client functions for it, documentation, whatnot. It's a really cool thing. And we're going to see how it's actually going to work in just a second. I don't know how you guys feel about software development. I kind of feel that it's going to collapse. Like we're slowly getting to that point in time where it's going to aggregate into this mass where everything just collapses, and Uncle Bob will be running, like I have my unit test. What the hell? I have a plan B for it, and that's alpaca farm. I already bought land, now I just need alpacas. But before I will have alpacas, I'll probably do what I can do right now is just write software for my little farm I'm going to have. So I want to write software which will be like a server in which I can sort of inspect like my alpacas, see how many alpacas I have, maybe inspect some details about each and every one of them, add a new alpaca to it. It's going to be fun. And I want to use servant for it. So this is initial things. We already seen that. So alpaca has a name, a color, an age, some colors that are apparently from Wikipedia. And ASIN instances, so because I want to represent my alpacas when I deal with my server as JSON. I want to provide them as JSON and retrieve them as JSON. So we've seen this so far. It's no longer magical. We know it will just work, right? But I want to have this. This is the server I want to have. So when I go to /alpaca and with method get, I just want to see all my alpacas all together. A map almost like for a key number 1, exists already right now 1 alpaca, and I have a status code 200. If I go alpaca 1 get, I get the single alpaca, and I can put new alpaca where the body of this function will be the JSON, and I have to provide the key. Right, pretty standard. There are libraries, not only in Haskell but in other languages, which will do that, without fuss. It will be just super easy. But servant is different, and it's different for a reason. And especially in the apocalypse world where everything collapsed, and like the new government will now pull all the regulations. Everything will be statically typed. You'll have protocols. Uncle Bob will be in jail. In that world, servant is the thing you want to use because it has a lot of magic. And the magic that it has is that when you define your server, it's different from at least any other libraries I've used before. Because when I used libraries before, when I was creating an HTTP server, I would always just instantiate it. I would say like, under this path, run this function. Under that path, run this function, and so on and so forth. Here, the only thing that we do is we provide a type that will represent our final endpoint. So here I'm saying I have a type which I called alpaca API, and I'm saying that, and by the way, this is a type. So I'm saying under alpaca / I will get a JSON, which is actually a map of integers to alpacas. Okay? I haven't written business code for it yet. I'm just encoding that information within the type. That is a standard Haskell type, nothing else. I can create another one, so I'm saying under alpaca / alpaca ID, I will get, so it will be a get method, I will get a single alpaca, and it will be encoded as JSON. And there's this additional operator in which we sum those two types together. So now my alpaca API is a type that represents those two types summed together. Finally, I want to put things onto my server. So under alpaca, and I capture the alpaca ID, there's going to be a request body of that put method, and it's going to be JSON, which is alpaca. And on the end, I'm returning. So put created means it's going to be put method with a status 201, and I will be not returning any content after this call. This is just a type. It's weird if you see this for the first time, right? Because what are those thingies? Is that a function? What the hell is that? It sort of like allows me to do this crazy thing, but for now, it's magic, okay? We run like we are in Hogwarts for now. So what can I do with it? Well, we also need this little thing. So if that's a type, we're gonna need like a proxy of Alpaca API. Proxy is this phantom type. Don't worry about it if you see it for the first time. The idea here is that sometimes you want to provide this type thing as an argument to your function, but it's a type, so you can really do that. So proxy just takes the type and makes it an argument. So, but if that just was weird, what I just said, don't worry about it. It should be just fine. We need this little thingy. All right. So what are the magical things I can do with this type? Well, for instance, I could create a client functions for my server. For the server which I don't yet have, because all I have is just type, which is weird. But I can create a client functions for it right now. What do I mean by that? What do I mean by client functions? Well, I could imagine that I want to have functions that represents the endpoints of my server for which some other programs or libraries can call. So getAll will be a function that returns a map of ints to alpacas, and that directly relates to that one endpoint that I have on my server. The getAlpaca takes an integer as an argument and returns alpaca, and that would probably call my endpoint on my server once I actually implement it. And the same thing goes for pulled alpaca. Whatever that M is something. That probably has to be like maybe a reader T, because we need to know where their server exists. Like we need to have access to configuration, right? So maybe like a host, the whole URL, host, and port is something we would like to have. Maybe it has in it some accept T because we want to deal with errors. But pretty much it's some effect. I don't really care right now. The nice thing about servant is that there's not much work I have to do to get those functions. This is literally all you have to do. You provide this one import, server client, you call client alpaca API, and that's it. You're done. And it works. It works. So we have all those functions, getAll, getAlpaca, putAlpaca, and they are already created. And we can now see how we can use them. So here I have a function which is called addNew, and it will just always, I will give it an ID, I will give it a name, and it will always create a new alpaca with a given name. It's going to be white, and it's going to be like a newborn, okay? So those two functions, I'm using those two functions which I just created a second ago, a putAlpaca and getAlpaca, and as you can see, that M is some client M. It's like reader T out of accept T. Doesn't really matter. In the main function, I have to provide the base URL. Based on that URL, I create an environment. After that, I call my addNew function with that environment, and I either get an error or result. That's all I have to do to create a application that will call my server. A server which, a reminder, still doesn't exist. Okay, with just a type, what other things I can generate? I can generate documentation without server still existing. So so the type already encodes a lot of information about what my server is doing, but like there are some elements from business logic that maybe it would be nice to have in the documentation, like tell somebody what, for example, alpaca ID is. Maybe somebody might be interested. So there are instances that we have to provide to servant. Like, for example, we have to provide capture alpaca ID int, and we say it's ID that uniquely identifies the alpaca in the system. We have to provide few instances for a type class called toSample, so where we show servant how the sample values of our JSONs that we're going to deal with in our system. So here one is one for alpaca and one for map from integers to alpaca. And having that, that's pretty much all we need to have. Now I can import the servant.docs. I can call the function docs with my alpaca API, and it gives me a thing of type API capital letter. I think it's a bit confusing. Maybe they should call it docs or whatever. But with that thingy, You can call them markdown functions. There are other functions that will create a different types of output. But we call the API docs with markdown. We save that to a markdown file. Later on, we produce PDF out of it, and there we go. We have a full documentation with all the methods being described. So here you have put. You know it captures Alpaca API. You know it has a request which will support the given content, which is JSON. You have some examples. You know what the response is going to be. All that for a server that still doesn't exist. From type, which I find really cool. Finally, the final magic is actually writing the server. By the way, do you know when I should finish? It's been 20 minutes, right? Is that 25 minutes maybe? Hopefully, okay. So actually writing a server. Okay, so this is our type one more time. Underneath here are 3 functions. Those are like dummy implementations, right? Like obviously in my super farm server, I would probably those will be like connecting to MongoDB and Kafka or whatever. That has to be super fancy. But for now, just let's stick with dummy implementations because that's not what's important. Here are the types. Like those are doing the whatever business logic I would like my system to be doing. Now the question is how I combined those functions with that type, so I get the server that will be for each of those endpoints call each of those methods that do the thing that they were supposed to be doing. As it turns out, it is as simple as creating something of a type server where you provide your Alpaca API and then just summing those functions together. And that's it. This works magically. Now, the really nice thing about it, if you mess things up, if you, for example, forget to provide one of those things, the code will not compile. Haskell will freak out, with those tremendously nice messages. But it's really, really cool to have that guarantee that, hey, no matter what I do, at the end of the day, compiler has got my back. I really, really like it. So that's pretty much it. Then out of this, you create an application, you call your main functions with the port, and the server magically works. Alpaca for you. Okay, chill. Because the next library is polysemi, after this Alpaca, there is a llama. Okay, you ready? Okay, so we have 20 minutes. We can do this. I think we're actually going to be on time, but I need you guys to focus right now. Are you able to stay with me? I have like 2 coffees, one after the other, so I'm ready. Okay, let's do this. Polysemi. So polysemi is a library for writing high-power, low boilerplate, zero-cost, domain-specific languages that allow you to separate your business logic from implementation details, and along the way, the logic that you write can actually become a library on its own. The central piece around which everything orbits in polysemi is this type called sem. I think it stands for semantics or just shortcut for polysemi. I don't know. But it's a type that your function can just return. This type is parameterized by 2 things, R and A. So when you see A, in this example, this is this integer. So when we have a function that returns a sem of A, it means that it's returning a program written in some DSL, and once that DSL is executed, it's interpreted, the thing that you're going to get at the end is going to be of that type A. So in this example, once I actually run this thing, I will get something of type integer, okay? And the other thing, the R part, is, so if sem is a program based on some domain-specific language, R is a type-level list of all the effects that define the vocabulary of my domain-specific language. So if you haven't seen this for the first time, if you see this for the first time, it's like a list with this little thingy here. So it's a type-level list. So we are saying on our list of effects, there is a console effect which has its own vocabulary, like I just did something with it. Oh, never mind. It has its own vocabulary like print line and get line. And there's another effect, random, which has an additional verb called next value, which gives you an integer. So those are the only verbs that were being used to write this program. We still don't know how the program looks underneath, but there are only 3 verbs that were, like the person who implemented this, he was able to use only those three verbs from those 2 effects to write his program. And normally, because that's a list, so it's like it has all benefits and downfalls of a list, so it's like a stack. So we are saying the first element of this list is console, and the second one is random. It's that set. So it becomes a pain after a while, especially if you like your compiler to help you out with some events, like you run all those things together. You will see why in a minute. But most of the time, we don't encode this way. Most of the time when we use polysemi, we encode this way. So we're saying our program returns a sem, which has a list of effects, and we are saying on that list, there has to be console, and there has to be random int. There might be other effects, and we say nothing about the order of how they stay on that list. We're just saying we are constraining our program that those 2 effects, they have to be there for this whole thing to work. Now, once we have this program, we can, let's actually try to implement that. So let's think for a minute, what are those 2 console and random effects? What are those? Well, let's look at console for a minute. How many of you guys here are familiar with GADTs? Okay, ADTs? Okay, more people. Okay, so I'm not gonna do like a 101 to GADTs, but it's almost like ADT, but the sole difference is that with typical ADTs in Haskell, not in Scala, in Haskell, when you create your constructors, your data constructors, you cannot say what type they're going to be. With GADTs, I can say, hey, my type is console MA. I have 2 data constructors, print line, which takes a string, and read line. But with this new encoding, which I have to turn on with a pragma, with this new encoding, I can say the type of the A. What is it? Here it's going to be string, and here it's going to be unit. With typical encodings of ADT in Haskell, that would be not possible. But if you see this for the first time and you're freaking out like, oh no, don't worry about it. Just stay with me. You have to write your vocabulary, your algebra like that. And with magic from template Haskell, you'd get 2 functions, print line and read line. And you see how print line was pretty much built out of the print line with the capital letters? So it gives you a function that will take a string and return you some sem, which just returns a unit. And on the list of effects, we need to have a console. Same goes for read line. It's just a new sem, which eventually, once it's interpreted, will give you a string. And the list of effects needs to have at least the effect console. That's it. I mean, great. We can do the same thing for random. One more time, we define what random is. It's going to give us a next random of type v. In our example, that was an integer. So, and we one more time call template Haskell to create those 2 functions. You could create those 2 functions by hand, but why the bother if template Haskell can do it for you? And yeah, that's pretty much it. What you get, that's all the code you need to have to finally write this program. Because, just a reminder, those 3 functions are generated for us. We can now use them. And because sem_r is a monad, we can write imperative style of programming in Haskell, which is great. Instruction after instruction. So I can say my program will ask you to insert a number. It reads that number from console. It then takes another number from next random, add those 2 together, modulo the possibility of freaking out because somebody gave something else than a number, but let's just ignore that for a minute. And there you go. Randomly generated, 1 from the user, from the input, add them together, return. That's it. Your program kind of makes sense, even though you still don't know how the randomizer works or how you actually will get that stuff from the user. And that's the problem, because when we run Haskell programs, we want to have an I/O of unit. But our program is some sort of like sem.ra. Great. Now what, right? Luckily, there are two functions in the polysemi library. One is called run. So just from the signature of this function, you can tell what it expects and what it will give you. So it's saying, if you have a program sem where the list of effects is empty, then I will just give you that A. Like that. There you go. If, however, you have, or if you have a sem which has one single element on that list of effects, and that effect is called embed of some m, then I will give you that m of a. So to be a bit, to be more specific, if I have sem of embed io of a, I will give you io of a. Magically, like this is a function that is implemented within the library itself, which is quite nice, and yeah, hooray, but I don't have any of those two, right? My sem has most likely console and random int, and I don't have embed io or an empty function. Now what? Is that it? Is that the presentation? What do we need is an interpreter. So we need to interpret all those effects. We need to tell compiler what it means to do input and output, what it means to take a random number. So, for example, for console, the interpreter, and it is also a really nice feature, just by looking at the signature, you can tell exactly what the interpreter is doing. It's taking your program that has a list of effects where the first effect is console, so it happened that the first effect is console, and it rips that effect. It removes that effect from that list. It gives you back a new program when that effect is no more. It's not there. And it can do it because along the way, while we're stripping that effect from that list, we are interpreting what should happen if we see one of those print lines or get lines, and we are interpreting it in terms of other effects. So, to give an example, I call the method interpreter. It takes a lambda, and that lambda is a function that goes from my data structure, so from console, to that sem of R. So I'm saying, hey, if you see something like print line, then just call function put string ln with that line and be done with it. If you see read line, then call function get line. Well, this thing will not compile because I was supposed to go from elements of type console into sem of R, but those two things return IO. Luckily, there is this effect called embed IO, the one that we've seen before. And that effect has one single method, and that method is called embed. So it's saying, hey, if you have something of m of a, and on the list of effects there is embed m, I know how to go from ma to that sem ra. So in our case, if you have IO of unit, and there is embedded IO on the list of effects, we're good, because I can go from IO of unit to sem r of unit. Are we good? Do you need alpaca? I don't have more alpacas, so I need to know, like, we're still here, like, you're with me, okay? I see some people nodding, some people already, like, tweeting. Right, so I have this. This is great, because now I've stripped completely the console from my list of effects. I've added that I required the embedded IO to be on that list. So I removed one thing, but I require the other thing to be on that list. So I could do the same thing for random, and it's exactly the same code. So I'm just saying, hey, you know, like, interpret this, and we're gonna remove the random int from the list of effects. If you see the next random, just call the random IO, which is a function from module system.random. And because that returns a IO, well, then embed it, lift it to sem r, and it works. Now, I can finally call my program, my function in main. So I'm calling execute. And what is execute? Execute takes my program and calls on it run console IO. Whatever comes out of it calls on it run random IO, so those interpreters, and at the very end calls run M. How does it really work? Well, it's almost like it. I lie a little bit here in this with these comments, but that's how I see it, and I think it's just better. So we're saying here our program returns a sem where the list of effects are console and random. With our at the very end we're going to return an integer, right? At run console IO gives us back what? It removes console from that list, but it requires the embedded IO to be on that list in the first place, right? Okay, the next interpreter removes the random effect and requires embedded IO, but embedded IO was already there. And as you remember, polysemi gave us this function. We have that function for free from the library, run M, which is saying if on your list of effects, the only thing that you have is embed of M, I will give you M of A. We have embed of IO, then by calling run M, we just get IO of int. And that's it. We show it, and the program works. Now, how can I test this? It's a tricky question, really. Because if you think about it, how on earth would I ever read the input that the user supposedly provide while I'm running this program, while it's supposed to be running on CI? Are we now supposed to hire somebody who will be just like entering values each time the continuous integration runs? And actually to reason about this logic, I need like the determinism on the random functionality, which is an oxymoron, I'd say. I mean, you know, think about random, right? But yeah, maybe that's actually what I need just for my tests, not for production. Because I can provide an interpreter just for my tests, which I will here call random const. It's an interpreter that takes that list of effects which is supposed to have random and removes that effect, but it also takes an integer as an argument. And I'm saying whenever somebody calls next random, just always give this one particular value which I gave you. Let's say 10. And that's it, like always like a constant, you know, random number generator. I can do the same thing for my console. I can say, hey, you know, like this is an interpreter that removes console from the list of effects, but it also takes a string, a line as an argument. So when somebody calls print line, we just ignore it, nothing happened. But if somebody calls read line, we always remove the same line. Having those two interpreters, I can now run my function. So I say like whenever you add two numbers together, one randomly generated and one from console, they should be added together. And I run this, so I have my list of effects. The first one strips the console, the other one strips the random, and what I have is just a sem of an empty list of int. And if you remember, there is a function on a library called run. If you have a sem with empty list of int, you will get that int, which is what we get, on which we can actually assert and be done with our work. So that's pretty much it. There are a few more slides ahead, but not that many, so stay with me. It's like almost to the end. I've only showed us like a lot of magic in Servant and in polysemi that runs on type-level programming, which is exactly the same as with generics, I think. So it is magical if you haven't seen how it works underneath, but once you start your little research, it becomes more or less engineering, less magic. But you, as a developer, you can make that decision. You can go a long way with just trusting that the magic works, because the magic is sound. The underlying machinery is just superb. But there's a lot of to learn if you want to understand how underlying machinery works. For that, I provide some links. So Sandy McGuire wrote this amazing book. I remember, I don't remember. I think it's now a bit more expensive than it used to be, but it's really worth it. I do encourage everybody, like, if you have a chance to read it, just read it. There's a very good blog post by Matt Parson and a nice workshop created by Thomas about types of specification. It's one of those workshops where you can follow along. You just go commit after commit, and you have like code examples and just some functions that you have to implement. It's a really nice experience to have. Now, what was the point of all this? This whole presentation, I think I've cheated because I promised polysemi. I've been talking about a lot of stuff. I truly believe that Haskell can be mainstream. I don't know if we want to have it. Like, there are people who be like, no, just stay with our little small bubble. But I do truly believe that it's a really nice language. And I've seen other languages with magic, but that magic is horrible. Magic that does not compose, magic that just simply doesn't work. It promises it will work, but it doesn't. A kind of magic that you try to do as something a little bit out of convention and everything just breaks to hell. This is not Haskell. I truly think that you can even write imperative software in Haskell, like the one have you ever, guys, like, have you seen in the slides a single bind method or fmap or whatever? You don't have to if you don't want to. You can. And that's the beauty behind the language. And also the beauty behind this language is the fact that the magic isn't really magic, it's just engineering, which I love. And my goal for the next, let's say, few months, maybe years, is to spread that love. And I would encourage you guys to spread it as much as you can. Write blogs, write libraries, do conferences, talk. Like, we really need this as community. Now, your homework, because there is homework, and I'm gonna check it. I have like a face recognition app running here. I know all of you. So for people, no, but for people who are interested, if you like what you just saw, it's late. I truly believe you will not remember anything I said tomorrow. Slides are on my Twitter. You should follow along. When you be going tomorrow home, just open your text editor, write a simple application, write your business logic in polysemi, instantiate a server, call that server, call the logic from that server from polysemi, add opt-arts, have ASIN, have it working, live through the pain, right? Because I only showed you the happy paths. There's obviously some pains along the way. It's not that perfect. Right? Always there are corner cases. But do that exercise and you'll be a happy person. And you will owe me a beer next time we're here. Okay, so where can I learn more? Okay, I probably have like 5 minutes, 2 minutes. So where can I learn more about polysemi? So this is like shameless self-promotion. So we can hack this homework together. If you like beer, you have Hangouts, and you have a Haskell installed on your computer. Let me know. We can do like a little 1-hour workshop online, as long as my internet works, because recently it's been weird. Anyway, there's a repository to the rest, which is like a simple CRUD application, but it combines polysemi with servant, so you can just I don't know, clone it and see how it works. Lastly, there's this little framework that myself and a few of my friends started, and it's if you're looking for a place to maybe extend your Haskell knowledge, you don't do Haskell for a living, but you would really like to do Haskell for a living. This is this project where you can actually do it, because we kind of combine different technologies. It's a little shame, because the idea behind this project is to make documentation easy by making the process of making documentation automatic. So like the idea is that you take code where all the knowledge and truth about your system exists, and generate out of it a documentation for free, have it on CI. If your documentation doesn't build, your product doesn't build. It's ironic, because we still don't have documentation on that product. It's just an empty README. But it's been only a few weeks, and like, stay with us. But the idea is you can gain a Haskell experience by helping us with this project, because you can pick any random technology. Let's say Elasticsearch, Kafka, whatever. You wanna put on your CV, hey, I know how to write Elasticsearch in Haskell? Great. You wanna have that experience? come say hi, and you can write a little plugin. The idea is to have this architecture pluggable, and then you'll have an entry in your resume, and then you can go find a cool Haskell gig. Now, I promised few folks that I will show how polysemi can conquer complexibility from different angles, like different dimensions. I didn't deliver that. I also promised that I will show how it's different from MTL and tagless final. What can I say? The approach that I have is the Soprano approach. The Sopranos is the show I recommend because you never really know how it's gonna. Maybe next year, if they have me, maybe some meetup. My name is Paweł Szulc, and thank you very much.